Oh,
Oh,
that was.
Well, hello. Welcome to the Space Oddities 3rd anniversary show. Thank you so much for joining us this evening. As always, if you're new here, you're especially welcome, and you join us on our 3rd anniversary, which is what I just said. So anyway, we've got the usual suspects here tonight, but let me just go around and introduce everybody again. So I'm Andy, obviously, and Michael, how are you?
Hi there, fine, thank you.
Daz.
Hello, how is everyone? Hope you're all fine.
It's all right. Roger, are you all right?
I'm ready for the after party.
Ah, yeah, that's the
EISCO.
Yeah. Lou, how are you?
Oh, just making my plans to move to Canada. Otherwise,
yeah. Anything we can do to help, Lou, just let us know. Yeah.
Thank you, guys.
Tom, nice to have you back, sir. Lovely to see you. How are you?
And lovely to be back. Thanks for having me back, guys.
That's okay. And I'd like to introduce this evening's special guest, Mr. Pete Williamson, without whom Space Oddities would never have happened. So he's the instigator of everything. How are you?
All those years ago, when we were young. When we were young.
Now you know how to blame.
Yeah. So we just had to ask Pete along tonight. I mean, he's welcome to drop in any time, but I thought we'd try get him along tonight to say an official thank you for everything, Pete, basically, because you started everything. You got us all together as a team, and we'd just like to say thank you. You can go now.
Well, you know,
so
I'm off. See you.
Is the old boot open?
And it's much better, Dad. You've got to come down now. It's much better.
Yeah, I'm thinking about popping over sometime.
They do the carnivore grill now, which is every type of meat you can think of. And
wow.
All types of roadkill.
Yeah. Anything that's walking past the pub.
Yeah. Fantastic. Well, anyway, so as you may have gathered, this is the 3rd anniversary. 3 years ago this week, we started Space Oddities and broadcast for the first time, or streamed, as I think the young people call it. And we had no idea then how long we were going to last, what we were going to do exactly. We just did it for the love of telling people about the universe. And I think, I think it's gone okay. Obviously, we would like more viewers. So please, everybody at home, get your phone books and start ringing people in the phone directory at random and telling them about Space Oddities. We need to spread the word, basically, because, we do put a lot of effort into what we do at Space Oddities. Don't forget, we have at the last count 517 videos on the channel. So we've done 517 videos in 3 years on everything to do with the universe. So don't forget to go and have a browse through those. And what have we got for you this evening? Well, as it's a special edition, we've got a few things lined up for you. We're going to have a competition, a sort of competition. What we thought we'd do is to say thank you to the people who send us their images for the gallery every week, for which we are eternally grateful. What we're going to do later, what I've done is to pick 10 images at random, as chosen by computer, from the gallery. And we're going to ask you, the viewers, to vote on your favorite. and whoever took that image will receive a Space Oddities t-shirt. So that's what we've got on the agenda, and we'd like everybody who's watching tonight, please, to vote so that it's a representative vote, and we'll come to that a bit later. Also this evening, as we are 3 years old, we have a theme tonight, and as you may have seen in the YouTube thumbnail, the theme is 3. So we're going to be telling you tonight about things related to the universe to do with the number 3. And we've got a lovely variety of stuff to tell you about. So that's coming up a bit later. What we're going to do, first of all, do the usual housekeeping. If you would like to support Space Oddities, you may do so in a few ways. You can click or you can scan the link here, the QR code, to buy us a coffee. Our caffeine intake is always in need of replenishing. So you can scan that link, or you can click the link that's just been put in the chat, and you can go to the Buy Me a Coffee page and buy some coffee. Much appreciated. Also, of course, don't forget you have the Space Oddities shop, and that has a bewildering variety. Well, not really. It has some t-shirts and sweatshirts. Sweatshirts, what am I talking about? Hoodies for you to buy with the Space Oddities design on it. And there are 2 designs that we've come up with. So that's the Space Oddities shop. You can get your lovely merchandise there. Don't forget, summer is here, and you need a new t-shirt. You really do. So go and buy a Space Oddities t-shirt. That's an order. So that's the Space Oddities shop. We'd obviously like to thank everybody who has donated to us. And, as I always say, all the money from your donations goes towards keeping Space Oddities on the road and working. So we are very, very grateful for your support in that. We could not do it without you. Equally, we couldn't have survived 3 years without you and your generosity. So from all of us to our audience, thank you so much for your generosity. And just do it a bit more, really. Just give us some more, and we'll keep going. So there we are. Okay, right. Well, let's move on. First thing on the agenda tonight is the news. So just let me sort this out. Give me 1 second. Actually, no, we won't do the news yet. I forgot what I was going to do. What I was going to do before we start is to ask all the panel here, and Pete, of course, have they got any reflections about the 3 years of Space Oddities? Anything you want to say about our 3 years together, bringing the universe to the masses, as it were?
I just think it's absolutely brilliant that, like when like I said, we ran Astro Radio for 11 years, and when I decided back in 2022 to call it a day, I didn't envisage how anything will continue, and you brought this together, and I think it's done an absolutely brilliant job, and it's well talked about. A lot of people talk about it, so well done, Andy, and everybody for bringing it together.
Thank you, Pete. Much appreciated.
I mean, I honestly felt guilty in closing Astro Radio at the time, because we had Reach Out and Touch Space, which was this format, but on the radio as well.
Yeah,
and we'd actually hit at the end of the tenure. We'd hit 2.5 million listeners, which was really, really good.
Yeah, it was.
We had we had listeners in Iran and everywhere. But I retired, and I decided, I've been an astronomer for many years, and I decided it was time to take a back seat, let's say. And I did. But you produced this, and this has really worked well, and it's like I say, it's well talked about, and I think it's brilliant.
Thank you, Pete. Thank you very much indeed. Yeah, I'll tell you what I miss a lot about Astro Radio, and it's a silly thing, really. I miss choosing the music for the week in space.
Yeah.
I used to love making those musical selections.
But I think that was the unique thing about Astro Radio. It wasn't just an astronomy station; it was a music station, and we used to mingle music with the astronomy. And I think that's probably a lot of listeners were music listeners, to be fair.
Well, there's this big overlap between music and astronomy anyway, isn't there? You find a lot
there is with me. I mean, I was a professional musician before I was a professional astronomer. So,
yeah,
I went from one to the other. So there is that overlap, so it does work well.
Yeah, I mean, you talk to a lot of astronomers. A lot of astronomers that I know are heavily into music, either writing it or producing it or whatever. And if they're not doing that, they're avid music fans listening to it. And there is this sort of affinity between not just astronomy but science and music. And I think they're really closely interlinked. There's also a link, of course, between astronomy and alcoholism.
I know that one as well.
No, it's true. Both of them have got 3 O's in the word for start. That cannot be coincidence. And both of them involve lying on your back staring through cylindrical objects. So, there is a...
But saying that, I remember doing a talk up at on the East Coast somewhere for poor money. And I was doing Herschel to Hawkwind, or Hawkwind to Herschel, whichever, or Herschel to Hawkwind as my talk. But Alan Chapman was there doing a talk on astronomy and alcohol. And
Really?
because the Royal Astronomical Society and the Liverpool Astronomical Society were founded by breweries. Believe it or not, I didn't know that.
Oh, wow.
They were founded by breweries.
It's just nobody could remember doing it.
Yeah, I remember it. But it was very interesting how astronomy and breweries were all interlinked as well, and a lot of astronomy societies, even Carrington, with the Carrington event, his wife owned a brewery. So,
Wow.
Really?
That's right.
yeah.
Well, of course, that's why astronomers look so old, because we're all pickled. We will never die.
Totally.
That's where we got our youthful looks from.
Well, we just carry on with the tradition, don't we, really?
It's rude not to.
It just has to be done. It just has to be done. All right. Anybody else got any thoughts about our 3 years together? I just want to say personally that I couldn't have chosen a nicer, greater bunch of people to work with than you guys at Astro Radio, probably. So,
I mean, it basically, I mean, I joined just before the COVID really kicked in, and basically it kept me sane. Well, some people say, oh, never was sane through the actual COVID years. So I thank Pete for that. But it's always been such a nice bunch of people. And like Andy, you had your program, I had mine.
Yeah.
I can't remember what I called it now, but there you go. The mind's going, it's the alcohol. But yeah, I had our own program. But it's like Pete said, we were able to put music in that with it, which really gave so much also to the actual shows themselves. So you had a music show, you had the astronomy side of it, you were the educational side of it, and it was absolutely fantastic.
Well, I used to play Astro Radio all day here at home because it was just such a great thing to listen to. And you heard lots of music that you probably wouldn't have heard either. There was some pretty eclectic music on Astro Radio.
Well, we were a victim of our own success because, as I said before, the more listeners you get, the higher the cost of the licensing fee is. And we hit 2.5 million listeners, which put the licensing fee up to, I think it was about £17,000 or £18,000 a year. And there's no way we could afford that anymore. I mean, we were getting fair bit of sponsorship to run it, but when it hit that figure, we couldn't continue. We became a victim of our own success. And because they monitor your listening figures, you couldn't fool them because it's all computerized. So.
Of course, yeah.
And I was going to say, I think we're using a really unique medium here with the internet, with YouTube, and the way we do the show. The way we actually have special guests. We have quite a few different guests on the show, and it's just a brilliant format that we do. We'll take part occasionally. Some more than others, I know.
Are you casting aspersions there,
no,
yeah. I feel a bit of a fraud though. I've only been here for less than 3 months, let alone 3 years.
Nothing personal, Tom. No, it's a brilliant format, and it is the way it's a free broadcast for everybody. those listening in and watching on YouTube. It's brilliant.
Well, can I just say, hang on, let me turn my brightness down. I look like I've been in an ice box. That's better. So, viewers, we need your help because having reached 3 years, we want to know where we're going for the 4th and subsequent years. We'd like to know what you want from Space Oddities. We'd like to know what you'd like to see more of on the channel. We'd like to know what, if anything, you'd like to see less of on the channel. Give us some direction, the things that you would really like to see us cover. Now, if you go to our channel and click the community tab on the channel, you'll see I've created a poll there where you can choose from 4 options about what you would like to see more of on the channel. Now, YouTube only allows 4 options, and it's not many. So if you want to suggest something that you would like to see us cover that isn't in the list of options, put it in the comments underneath. And indeed, any feedback about the channel, put it in the comments underneath. I created that poll a couple of days ago, and so far only 8 people have answered, which is not a representative sample. It doesn't allow us to do anything. So please, can you, if you do us that favor, go to the YouTube channel, go to the community tab, and just fill in the poll. That would be great, and that'll give us some idea of what you, our viewers, want to see, because you are our audience, and we want to give you what you would like. So
because if you don't, we will. So
yeah, exactly. So take that as a threat.
That's democracy.
And talking about our viewers, can I just thank everybody for their very generous donations tonight?
Yes, indeed.
Thank you, everybody. We do appreciate it. As Andy says, all this money goes straight back into producing these shows because it all costs money. And just thank you very much. It's so
far, I would like to say thank you to Alan Ledbury. Thank you, Alan. The Deep Burrito, thank you for your generosity. Ian McIntyre, thank you. Paul Bogart, thank you. And thank you. What can we say? Oh, and Gerard as well. Thank you, Gerard. That's very kind of you. And we do appreciate it. And the more money we can accumulate, the better our production will be, and the more things we can do. But we do want to know where we take Astro. I keep saying Astro Radio. It's Pete's fault. I've got Astro Radio on the brain now. So we do want to know where to take Space Oddities over the next year. So any ideas, any thoughts, do let us know. Alternatively, if you don't want to fill in the poll, you can email us anytime at info@spaceoddities.space. So please do let us know your thoughts, because we will try and accommodate them wherever possible. So there we are. Okay, well, let's finally move on. Let's go to the news. So some really interesting news stories tonight. So let me just set this up. Give me 1 second, please, and we'll have a look at the news for the 27th of May, 2025. So the first story, it's funny, we were talking, if you were watching last week, you'll realize I was talking about how we can fix the problems with cosmology that the JWST has presented us with, and how the JWST has found incredibly distant, incredibly early galaxies. And there was one that was a record holder. Well, would you believe it, this week there's a new record holder for the most distant galaxy ever discovered. And that goes by the name of, believe it or not, let me just put this up, Mum Z14. This was announced this week. You can see in the picture, it's in that blue panel, and it's just a collection of pixels, but it's definitely there. It's so far away that it appears like that. What about this galaxy? It holds the record. It's got Lou, we were talking about this last week, weren't we? The redshift. The redshift of this is 14.44. But what that means is it's approximately 280 million years after the Big Bang, which means its light has traveled for over 13.5 billion years to reach us. Wow. So this is the new record holder, but it's a bit strange. So not surprisingly, the galaxy was identified using the JWST. Now they're doing this survey called the Mirage or Miracle survey. And what this means is they're looking at galaxies and asking if they're a mirage. In other words, is there some sort of problem with the measurements that make them appear older than they are? Or are they a miracle? are they really that old, ancient, and far away? And this was taken with JWST's NearSpec instrument. This galaxy is unusual because it's notably luminous and compact, and its diameter is about 482 light years across. And this suggests intense star formation very early in a very small region. And again, this challenges our current ideas of early galaxy formation. So there's another thing about it that is really interesting. It's got a high nitrogen to carbon ratio. This is what we tend to find in ancient globular clusters. So are we looking at an ancient globular cluster in formation, or would we classify this as a galaxy? What this does indicate, or should indicate, is that there were supermassive stars very, very early on in the universe. And of course, the subsequent chemical enrichment processes much earlier than we thought was possible. So again, another spanner in the works from this galaxy. And this does suggest that all of this happened much earlier than we thought. So as we were talking about last week, there is something going on here that we've either got wrong or we've misunderstood, or something we don't know about entirely. That there could be some process of star formation of which we're completely unaware that was around in the early universe but isn't anymore. So that's really interesting. The other thing about it is there's no active galactic nucleus. In other words, there doesn't appear to be a supermassive black hole in this galaxy either. So this is a very early galaxy without a supermassive black hole. And again, it's going to just raise loads of questions. So that's a new record holder for the oldest and furthest galaxy yet discovered.
Just two things on that, Andy. Did you say it's carbon rich?
What I say on, let's just go back to it. No, I said that there's a high carbon to nitrogen to carbon ratio. So I can see it now. Yeah, sorry, I couldn't. It's the ratio between carbon and nitrogen.
Yeah, and just another couple of things. If you put the big picture up again, if you squint, it's like one of those magic pictures. You can see a penguin.
Ah, yes, that's true. Dad's lay off the weed, mate. So there we are. Okay, right. And talking of discoveries, another great discovery this week. There's a new trans-Neptunian object, and it's a big one. So trans-Neptunian objects are these objects beyond the orbit of Neptune, going out to the Kuiper belt, and astronomers have discovered a new one. This one has the rather fantastic name of 2017 OF201. Trips off the tongue, obviously. I'm sure it's going to get a better name in time. It's a potential dwarf planet. This could be a dwarf planet. And if this is a dwarf planet, then it's the second biggest TNO, or trans-Neptunian object, after Pluto. So it's really big. And this was discovered through observations from 2011 to 2008 with a telescope in Chile and the one in Hawaii. It's about between 550 and 850 kilometers across. So this does put it in the range of known dwarf planets. It's probably spherical, and it's probably, like we suspect most of them are, a ball of ice and rock. But it will be, if it's confirmed, it will be the second largest TNO, only second to Pluto. But what's interesting about this, well, there are two things interesting. Its orbit, its ranges from 45 astronomical units, and Pluto is 44 on average, and that one astronomical unit being the distance from the Earth to the Sun, of course. But its aphelion, its furthest point, is 1,630 astronomical units.
Wow.
So 1,630 times the distance from the Earth to the Sun, which means it does that orbit into the solar system and out again in about 25,000 years. And this, how did it get into such a weird orbit? Well, the only thing really that could have done it was an ancient encounter with a giant planet that sort of pushed it into that strange orbit, but obviously we don't know at the moment. And in fact, that distance of 1,630 AU puts it about the edge of the Oort cloud, the inner edge of the Oort cloud. So it goes from inside the orbit of, around the orbit of Pluto, roughly, out to the Oort cloud, which is an incredible orbit. I'll just show you a visualization of that in a second. So what else? Yeah, now the bad news is, we've heard a lot about Planet 9 recently, this clustering of Kuiper Belt object orbits, as if they were being pulled on by a planet, this so-called Planet 9. Only 2 weeks ago, we learned that astronomers may have actually visually discovered this Planet 9. But the fact that this 2017 OF201 has maintained such a stable orbit for probably billions of years seems to indicate that that Planet 9 is not there. Otherwise, it would have kicked it completely out of the solar system. So this could throw a spanner in the works of Planet 9. Nothing else much there. Okay, they're going to do further observations, obviously, but whatever it turns out, it will enhance our knowledge of the outer solar system. So let me just show you this orbit of this incredible object. So if you look in the inset, you've got the orbits of Neptune and Pluto shown and 50 AU marked on the inset. And then the smaller size of that, you see the orbits of Pluto and Neptune, and you see how far out this object goes. 250 astronomical units is the scale. So it was 1,600 and something. So it's touching the inner edge of the Oort cloud on its aphelion, the furthest point from the sun. So this is a really significant discovery, and let's hope they come up with a better name for it soon. So there we are. Well done to LIGO. LIGO 04 records 200th detection. What's this all about? The LIGO, the Laser Interferometer Gravitational Wave Observatory, which obviously made the first detection of gravitational waves. It's been going through an observing run since May 23. And this observing run is going to end in October. And it's just made its 200th gravitational wave detection in observing run 4 or 04 or 04. So most of these detections have involved mergers of massive objects like black holes and neutron stars. Some have yet to be identified. But just to give you a comparison about how the detection rate of gravitational wave events is accelerating, during the first 3 observing runs between September 2015 and May 2020, the total number of those 3 ones was only 90, the total number of detections. So in the past 2 years, it's made 200 discoveries just in this observing run. So the technology's moved on now, and LIGO has been upgraded so that we're detecting these mergers of massive objects much more frequently. Cosmic Jousting is the name of the game. This is a combined ALMA and ESO image of a pair of galaxies 11 billion light years away. These two are locked in a gravitational dance because they will finally merge. And as you may know, with galaxy mergers, they come together and they sort of zip past each other and get pulled back and go out again. And it's a dance which takes place over millions of years. What's interesting about this particular dance is, if we have a look at the artist's impression, the galaxy on the right, it is a quasar. It's got an active galactic nucleus, and it's shooting a jet of plasma right out of the galaxy into the heart of the galaxy on the left. So it's sort of like a lance in jousting. It's spearing it. What does this mean? What's happening? What this happens is that the clouds of hydrogen, the molecular hydrogen in the galaxy on the left, are being dissipated by this beam of radiation from the other galaxy, so that they will not form stars. So the galaxy on the right is actually quenching, as it's called, the ability of the galaxy on the left to form stars. And that's pretty bizarre. So I just thought I'd show that because that's really, really interesting. It's a cosmic jousting match. Lovely image from Mars. These weird streaks on Mars that virtually every spacecraft has ever orbited Mars has seen. These streaks are seasonal. They appear in different seasons on different hemispheres of Mars. But the question has always been, what the hell are they? And I don't know if any of the panel here tonight have got any suggestions as to what those are.
Wasn't it melting ice or the sort of water, if I remember? Well, that was one of the theories.
Yeah, that's right. A long time it's been thought that they might well be releases of briny water on the slopes, because these always occur on slopes. And that's been the prevailing idea for a long time. But now astronomers or planetary scientists have used machine learning to process every single incidence of these streaks from thousands and thousands of photographs, a lot of them taken by the Mars Reconnaissance Orbiter, but also Mars Express and the other orbiters. And the machine learning has told them it's got nothing to do with liquid, it's dust. Oh. And these are darker layers of dust under the surface that sort of spill down the side of these slopes due to, wind or I was going to say Earth movements, Mars movements, Mars quakes. And so what we're looking at is darker dust that was underneath the top layer there, that's sort of just fallen down these slopes, which is a bit of a shame.
I've seen these before on the surface.
Yeah.
And as you mentioned, there was some thought that it was high mineral content water. But we actually have a time sequence of these. This is a single image, but we have time sequences of these markings changing indeed over fairly short periods of time.
Yeah, that's right. Well, the conclusion now is that it's dust, basically, not any liquid, which is a real shame. But beautiful images nonetheless. I mean, very striking images. So that's obviously yet to be confirmed. It's in a paper that came out last week. But they've analysed, I think it was 68,000 images of these streaks, if I remember correctly, and they basically asked the AI, what are they? And this was the conclusion that it's dust.
So Andy, can I ask a question, or Lou actually might know? So this is obviously a black and white image, but what's causing the difference in coloration between the darker area at the top and the lighter area?
Well, I would guess that would be the top layer being sort of bleached by the sun, if you like, or by the ultraviolet.
It could be. It could be a particle size difference causing with a different scattering function. The dust that we see on the surface of Mars is extremely fine, like talcum powder, like baby powder. So if there were other minerals in this, it would have different scattering properties, might look different.
Yeah, that might be it as well. So anyway, interesting discovery. Moving on. This is a rare thing. This is a supernova explosion. It's a Type 1a supernova explosion, but it's perfectly spherical. And this is very, very unusual. Now, this object, we don't even know how far away it is. Estimates vary from 300 and something light years to 700 and something light years. And it's an ancient supernova remnant, but the fact that it's spherical is very, very strange. And the other weird thing about this is there are no X-rays associated with this. It's only visible at radio wavelengths. So no other type of telescope could see it. No X-rays, which is what you nearly always get with supernova remnants. And it's only visible at radio wavelengths. So this is a bit of a conundrum.
So then,
I don't know if anybody's got
then what would be the evidence that it's a supernova? Because you're right, you're violent and hot.
Yeah, it is. It's hot. And also they think they've identified a progenitor star at the center of it. So what they're thinking is that, that with a Type 1a supernova, two things can happen. The white dwarf can either be blown apart completely, or it can be what's called a zombie star, where it undergoes repeated detonations in the cycle of the supernova. and it could be from that, which might indicate why there are no X-rays. I'm not quite sure why, but they say that if it were a zombie white dwarf, there wouldn't be any X-rays.
I mean,
So,
that looks like a perfect inflation, doesn't it? Of some sort.
Yeah.
That is very
Yeah.
strange.
Yeah, and it's only visible at radio
Yeah.
wavelengths. There's no visible light at all. It's only a radio object. So really bizarre. Anyway, just thought I'd show you that. And then lastly, countdown to Apophis. Now, don't forget that in 2029, the asteroid Apophis, which is one of the most, if not the most dangerous asteroid to the Earth in the solar system, is going to make a relatively, a very, very close pass by the Earth. And it's not going to hit the Earth on this occasion, but it could well do in the future. So we need to know everything that we can possibly learn about the asteroid from this encounter in 2029. But there's been a conference this month in Tokyo about this. And scientists from 31 countries got together. And what the conference has done is to issue a warning that the world isn't doing enough to prepare for this perfect study opportunity, to learn as much about this asteroid as we possibly can, because it has a distinctly non-zero risk of colliding with the Earth in the future. And the only spacecraft that are going to Apophis at the moment are Destiny Plus from Japan, Ramses from the European Space Agency, and the diverted NASA's OSIRIS-APEX, which was OSIRIS-REx, of course, but that now its next part of its mission is to study Apophis. And what the scientists say is that this just isn't enough. We must send smaller missions, including CubeSats and small sats, and basically get everything out there that we possibly can to study this asteroid in minute detail so that we can learn about it if it threatens the Earth in the future, which it undoubtedly will at some point. And also they say, look, the students also need to lead these programs. Students, the next generation of planetary defense experts, needs to be involved with this as well, and because they need to learn how to do it. So this is a wake-up call, just basically saying, wake up, time is ticking down to the encounter, and the world is not ready to study this asteroid as we should be doing to learn more about it, so we know what to do with it in the future when it threatens the Earth. So there we are. That's a wake-up call about Apophis. We will, of course, be covering the Apophis encounter in 2029 here on Space Oddities. So there we are.
I know the Americans have a procedure. If that's because I can remember we were looking into it ages ago when we were doing one of our radio shows, and they do have contingencies plans for what's going on. But it's like they said, they can only make contingency plans for objects that are going to hit us if we get enough warning that they're coming. And of course, if they're coming from the sun, we tend to spot them later. And also, it's like they say, you know, there's some speculation there. Should they tell the population this, that, and the other? But one of the things is that once the object if it's too big, then there's nothing that can be done, especially if you haven't got any time to even try and deflect it. But I know the Americans have got some contingency plans because I ran through them. I had a read of them, and that. So I'm not. You probably find other governments have got some sort of contingency plan. Yeah, I mean, one day the odds are. I mean, we've escaped this for a long, long time, but the odds are at some time we may end up getting, you know, clipped or hit by one of these things. But
well, especially Apophis, because it returns every few years, and it's the most dangerous object, as far as we're concerned, most dangerous object to the Earth. This is why we need to study it in great detail.
It'll be interesting to see when Osiris Apex gets out there and we get some images of what this thing's actually is. So,
so there you are, guys, audience. Thank you so much for your comments, and it's great to see you. Gerard's back. Gerard has not been well, so Gerard, we hope you're feeling better, mate, and thank you for being here. And And yeah, so we hope you get better soon. So I'm sure everybody here wishes you the speedy recovery. And so there
Andy,
we are.
Andy, I was gonna ask
Okay.
a quick question before we go on. How big is Apophis in relation to giraffes?
It's 346,000 sea lions. So I don't know what the sea lion to giraffe conversion factor is, I'm afraid. Give me a second and I'll find that information for you. But it's
Here to serve.
But it's yeah, absolutely here to serve.
Do the sea lions know that?
Well, no, I don't think they do. But perhaps somebody can look that up. The size of a diameter of
340 meters.
Oof.
There you are. So capable of doing a lot of damage. Yeah. So there you are. David says we should land on it too to set up comms. Absolutely. Definitely. And great. And it's so lovely to see everybody here tonight because we've got quite a few people in tonight. So there we are. Okay. So let's move on. And we come next to regular feature. Before we get on to the main feature of tonight, we'll go over to Roger, if Roger is ready.
Yes.
Ready, willing, and able.
Well,
very on.
well, maybe 2 out of 3.
Okay, take it away, Roger.
Okay, so we're going through the end of May and starting into the start of June, the start of the summer season. So we'll, well, if we could get a summer. So we're currently experiencing a new moon and gradually working our way through the next week to the first quarter. So that's good. So the skies are a little bit barren of planets. We've still got Mars, although it is a rather small object at the moment. But we've still got some of the spring constellations showing quite nicely, especially the galaxies of season of Leo and Virgo there. But we are now starting to experience the summer triangle coming up later in the months, and also the Milky Way with the 4 coming up somewhere in the middle of the night. So that should be quite interesting. And we're
fantastic.
So, hang on, wrong presentation. So as we gradually work our way through, as you can see, the Milky Way is gradually making an appearance through the days, and that will be great for us. Before sunrise, we've still got the majority of the planets coming up through, although Venus will probably be the only one that most people will be able to spot, recognize quite well, because the other ones will be too small or too faint compared to the morning glow of the sun. But they're all gradually working their way through. So all well and good there. Right, so we do have an interesting gallery, although it is only from 2 contributors. So you'll have to bear with us on some images from Kenneth and from Tom. But here's the first one that Kenneth's done. He's been busy on the large telescopes again that he's been using, the 2-meter telescopes from the Liverpool. And this is a lovely, a nice detailed shot of the Crab Nebula.
That's nice.
Oh, that's nice.
That star at top left, you could have got all of it.
Yeah.
For goodness sake.
He cropped it out, or tried to crop it out.
Yeah.
Don't waste the telescope.
Yeah.
That's lovely. That's a great image.
You've done well there. And then we've got something which I hadn't heard of before, the Fossil Footprint Nebula in Perseus. Yeah. And this was done in Las Palmas.
Oh, nice.
Ooh. Wow, that's lovely. Look
Yeah,
at
I see there's like a bow shock effect on that star there.
Yeah, definitely.
So,
a lot of radiation there.
Yeah, absolutely.
Blimey.
So, yeah. That's one I've not seen before. Certainly never heard of that one before anyway.
What did you say that was? Sorry?
The Fossil Footprint Nebula.
Well, in Perseus. So that's not surprised I haven't.
It's quite
Yeah.
a different image, actually.
Mm. So,
Worth having a shot.
well, I'm sure it would be a bit difficult with our smaller size telescope. So the 2 meter is obviously helped to resolve that small object. But there we go.
Yeah.
He's managed it. Well done. And then we've got the Phantom Galaxy M74 in Pisces. And
Oh, look at that.
Ooh,
look at that one.
Look
nice
at that.
colored.
Very
Yeah,
amazing.
beautiful. Very, very blue-white stars there, aren't there?
Absolutely.
Was this with the 2 meter?
Yes.
Oh,
well.
that is lovely.
My goodness. It's either that or 17 days of integration time with the sea star.
Anyway, moving on. And we've got this one of NGC 1931.
Ooh.
Oh,
Nice nebulosity.
I'm going to screen grab that one. I've never heard of that one before. That's nice.
that's beautiful.
Okay.
I'd like to put a framed image of that on my wall. That's beautiful.
Yeah.
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 One of those metallic prints would be good, wouldn't it?
Well, I know Kenneth has been trying to sell some of his camera gear, so I think it might be perhaps a deposit for his 2 meter telescope somewhere. I think we need to.
Well done, Kenneth.
Yeah.
That's excellent.
Yeah, he's only got a few more £1 million to get for one of those 2 meter telescopes, I'm sure. So our other contributor is Tom, and we've got some interesting images here. The Valentine's Rose Nebula in Cepheus, and this is in sulfur and hydrogen. 18 hours.
18 hours.
18 hours. But look at this.
Oh, that's nice.
Wow.
Wow.
That really
There
is something.
There is
Well done,
oxygen in
Tom.
there a little bit, but only a few hours. So
Mm.
I'm really, really chuffed with that one.
Yeah.
I should think
nice
you
one.
would be.
Nice
Yeah.
one, Tom.
Mm.
That's nice.
I can't quite
nice.
see the rose, though.
No, I don't.
Sure it's there.
I can see a Venn
Yeah.
diagram, but I can't see a rose.
Okay. And another one from Tom of the Wizard Nebula. So haven't managed to image any O2 on this yet. So he's done a bit of fiddling. So this is the result. And here we go.
Oh, that's nice.
My
Oh.
gosh.
That's amazing.
There's some nice details in there as well. Actually, you can't really see on that screen grab, but there's some nice details round about the center of that one. So
Yeah, it's beautiful.
Mm. Well done,
A lot
Tom.
of contrast and range.
yeah.
Mm. Okay. And another one from Tom of the Elephant Trunk Nebula. This is 15 hours, this one, on his Skywatcher.
Oh,
Is that the latest one that you bought, Tom, the Skywatcher 200p?
No, the Jings, I bought that about 4 years ago, and it itself it's quite an old scope, but bought it from you. But
There we go.
Just put that alongside a Hubble image. You can't tell. the
oh
difference.
yeah, that's brilliant.
Yeah, absolutely.
Mm.
I like that one.
Maybe it is a Hubble. You better check it. I'm not sure.
Yeah, right.
cheater.
Yeah, he's taken the water. He's taken the watermark off.
I used ChatGPT to remove the watermark.
Yeah.
Mm.
Wow.
Okay.
Wow.
How
that's
long did you
amazing.
say? 15 hours?
Yeah, 18 hours. That one.
15 hours, yeah.
15
Yeah.
hours? From a,
Over a
That's 5 hours of each.
Wow.
Yeah,
Mm.
Wow.
there's
Yeah.
a nice depth in that one as well. I'm quite happy with it.
And then we've got a crop of nebula. Now, this is one that he has taken, and it is not a Hubble.
It's nice.
Wow. That's just
If you
gorgeous.
Well, that is lovely.
If you do compare it with the Hubble, it's very similar.
Oh, really? I'll take
Yeah.
that. I'll take that.
Okay.
Yeah, I'm sure. I'm sure.
Mm.
I'll try and double the time just to increase the detail a little bit. But yeah.
I mean,
I love the whole.
yeah,
of
the
it.
whole looks
Oh.
three-dimensional, doesn't it?
That's,
It really
Yeah,
does.
really
Really
does.
nice.
that's a
text as
nice double star at the bottom as well, isn't it?
Mm.
Mm.
well. Oh, yeah.
Mm.
God.
The Skywatcher 200p, is that, I thought that was a Dobsonian,
It's a Newtonian, yeah.
Mm.
but maybe not.
Yeah. Mm.
That's
You can get a
beautiful.
dog version of it, I think, Lou.
Yeah.
Wow.
So,
well done.
so that concludes the What's in the Night Sky with the gallery from Kenneth and Tom.
Well done.
Well,
Yeah.
listen, guys, well done. Well done to everybody, because those images, as always, are fantastic, which is why we look forward to seeing them, which is why you should keep sending them in. So attach them to an email, send them to gallery@spaceoddities.space, one image per email, please. And as well as appearing here, you have your own gallery on the Space Oddities website, which
Well
is
done, everyone.
https://spaceoddities.space. And you have your own gallery, so you can show off to people, saying, look what I've done. So well done. Keep the images coming in. We love them. And we now have a total of 186 images in the gallery so far. So let's see by next week if we can reach the 200.
Hey.
So there's a challenge for you. Get us up to 200 images by next week. Send those images in. And we can celebrate. We're going to have another celebration next week. 200 images in the gallery. So there we are. Oh, any excuse for celebration, me. That's what I'm all about. So anyway, we are going to move on a related note now. We thought we would like to do something to say thank you to our photographers who send their images in, whose hard work, brilliance, and technical skill is, as you will agree, stunning. So what I've done, I have chosen from the gallery 10 images at random, chosen by computer. We would like you, the viewers, in the chat to tell us which one is your favorite. And let's see whether we can get a winner out of this. And the winning photographer will receive a Space Oddities t-shirt. So what more do you need, eh? So I'm going to show you the presentation now. I've given each image a number. So all you have to do in the chat is to put the number of the image that you think should be the winning one. Simple as that. And if you could all get involved with this to make it a representative vote, that would be smashing. All you have to do is put a number in the chat. Couldn't be easier. So without more ado, we will go to the first image. Just give me 1 second. And here we go. So there is your first image. Does anybody recognize that panel? Any idea what that is? M78. It's M78 in Orion. Now, I haven't put the name of the photographer against each image. I'll show you those later because I want it to be a surprise. So this is image number 1. So moving on to image number 2. Anybody know what that is?
It's not
No?
a coin, is it?
M90.
M98. This is M9 Galaxy M98. So that's your image number 2. It is, isn't it? Image number 3. I don't think that is an introduction.
Rosetta.
Yeah, that's the Rosette Nebula, image number 3. Beautiful image again. These are all fantastic images. I think the computer chose well. The computer chose wisely.
Pleiades.
Hey.
The Pleiades, number 4. Lovely image of the Pleiades.
Definitely.
I love how
Yeah.
we can get this stuff from our back gardens. Isn't it amazing?
Mhm.
Absolutely.
Isn't it?
It's witchery. It's witchery.
NASA plugged
Yeah.
them into our telescopes. That's what it is.
Mm.
Absolutely. So that's image number 4. Image number 5.
Ooh, M51.
Ooh.
Yeah, that's M51.
the world.
Yep. That's your image number 5.
Very nice.
Pretty.
Ooh.
Image number 6.
Tiny M51.
Same thing, but much wider angle, which I love that image. It's it's beautiful.
Yeah.
I love that you can see other galaxies in this image as well, which is it's lovely image. So that's your image number 6.
Oh.
Image number
love it.
7.
Love it, love it, love it.
Ah.
Very creative, and that image has the title Orion brackets call the Doctor,
Yep.
which is lovely. I love that image.
Yeah.
That's lovely.
Blurring
So that's-
blurring the focus on that really shows the stars there.
Yeah.
Yeah, the colours
And the
brings
colours.
the colours out really nicely.
Look at metal does.
Mm.
So you can see the color very clear. But lovely creativity there.
Oh, that's
Image
nice.
number 8
Nice.
Wow.
needs
The
no
horse,
introduction.
yeah.
Horsehead and Flame
That's
Nebulae.
nice.
That's beautiful. That's your image number 8. Image number 9.
Mm.
Ooh.
I love the sense of scale in this one. With the foreground, it's so massive, you know. It's just fantastic.
And they managed to do it without a single Starlink screwing it up. That's pretty good.
Yeah,
That's not normal.
yeah,
And you can
No,
see my
that's
house.
Yes.
yeah, yeah. So that's obviously star trails, and finally, image number
Finally,
10.
a planetary image.
Yeah. And that, of course, is the Lunar South Highlands. So that's your image number 10. I'll just go back through them briefly. So that's number 10. Star Trails at number 9. Horsehead and Flame, number 8. Orion Call the Doctor, number 7. M51, number 6. M51 again, number 5.
Olaf.
M45, the Pleiades, number 4. Rosette Nebula, number 3. M98, number 2. And M78, number 1.
Amazing.
So just go through those one more time, just very briefly. M78, M98, Rosette Nebula, Pleiades, M51, M51, Call the Doctor, Horsehead and Flame, number 9, Star Trails, and then number 10, Lunar South Highlands. So viewers, there are your 10. If you could please put the number of your favorite, the one you want to win, in the chat, and we will come back to those later to announce the winner. So if everybody could do that who's watching tonight, that would be fantastic.
Do you want us to vote as well,
So-
Andy? Do you
Sorry?
want us to vote as well?
If you like, yes, why not? Why not? So you can put your numbers in the chat as well. And there we are. So we've got some votes coming in already. Keep them coming in, please, so that we can choose a winner who will receive a fantastic Space Oddities T-shirt. And there you are. We'll announce that a bit later in the program. So now we are going to move on to the presentations for tonight. As I said at the beginning of the program, to commemorate our 3rd birthday tonight, we are going to tell you about things in the universe relating to the number 3. So if you just give me 1 second to set this up, I will go first. And here we go. All right. Hope you're enjoying the show so far, viewers. And, any feedback, comments, anything, don't forget to put them in the poll on the community tab of the channel, or send us an email at info@spaceoddities.space. And here we go. So I've called my presentation, fairly obviously, 3. So what are my 3 things relating to the number 3 to do with the universe? Well, the first one is the so-called 3-body problem, a classical problem in astronomy. So you start off with a planet orbiting a star. It's got more or less a perfect circular orbit, a little bit elliptical. But the point is you have one body orbiting another body. Well, there are, several planets shown here, but they are all 2-body systems. The point about this is these orbits are stable. They are predictable over very long periods. You can predict the orbit of a planet orbiting a star to a high degree of precision over a very, very long time indeed. So this is what we're used to. But when you add a 3rd body into the system, something happens. So here you have 3 bodies orbiting each other. And as you can see, what happens is that the orbits become chaotic. In other words, unpredictable. And although you've only introduced an extra body, it has introduced a degree of instability into the system so that you cannot predict over even short periods what those orbits are going to do. And adding trails here, you see what actually happened. The orbits are inherently unpredictable. Now, what about if we start this again, but change the position very slightly of just one of those bodies, the initial position of one of those bodies? Well, what you actually get is something completely different. So even a tiny change to the initial position of one of those bodies introduces a completely new set of chaotic orbits. Now, you may be familiar with this idea because this idea is known as sensitive dependence on initial conditions, and it's the cornerstone of chaos theory. Can anybody else, I'm sure one of the panel will be able to tell me a very famous example of sensitive dependence on initial conditions. What's it otherwise known as, or commonly known as?
The butterfly
It's commonly
effect?
known as the butterfly effect. Yes, it's the butterfly effect. The idea that a butterfly flapping its wings on one side of the world can affect the weather on the other side of the world. It's a chaotic system. So the 3-body problem means that if you have 3 stars co-orbiting, you cannot predict the orbits of those stars most of the time. What do I mean by this? Well, here we have a system called LTT 14445AB, and it's a triple star system. Here's a view from a hypothetical planet in the system. And there are 2 stars orbiting each other, but that large star is orbiting both of them. And this can lead to completely chaotic orbits. Another example is GW Orionis. Now here you have 3 stars. Again, you have 2 smaller stars co-orbiting, but another star orbiting them both. Now, this is a simulation of what it looks like. The planetary disk, which is going to form planets probably one day, all that dust, as you can see, is being severely disrupted by the orbits of those stars. And the great thing about this is there's a planet in there. A planet was recently discovered in this system that is orbiting all 3 stars. So the orbit of that planet is going to be pretty much unpredictable. So what would it be like to live on a planet like that? Well, this is going to be a very, very strange planet to live on, because it will come under all sorts of weird gravitational influences as it orbits all 3 stars. Now, you may be familiar with the books and the science fiction series that's been on TV called 3-Body Problem, which was, if you haven't seen it, absolutely fantastic. And it takes this idea of a planet that orbits 3 stars that goes through all sorts of cataclysms and earthquakes and gravitational influences as it orbits around these three stars. But GW Orionis is a stable configuration. So although it's three bodies, because the two stars are closely or close together, it's actually modeled as a two-body system because they're so close together, they actually function as one gravitational well, if you like. So although there are three stars, this is actually a stable system. But a planet orbiting all three stars is going to go through a hell of a lot of changes, obviously. But there is a system with a completely unstable configuration, and that's HD 98800. This is a chaotic system where you have two small stars and two other stars. This is a four-body system, and this is completely chaotic. The orbits of these stars is inherently unpredictable. So there you are. That's the three-body problem. Three bodies or more leading to orbits that are completely, even in the short term, completely unpredictable because of this this initial sensitivity, the dependence on the initial conditions. Even if you change one thing very tiny, it has massive effects on the whole system. Moving on to my next one, three quarks. And to start off with, I'm going to give you a quote from James Joyce from the book Ulysses. Three quarks for Muster Mark. Sure, he hasn't got much of a bark, and sure, any he has, it's all beside the mark. Anybody who struggled through Ulysses, as I did as a teenager, will recognize that. This is where the word quark first appeared. This is exactly where it first appeared. And for those people who insist on pronouncing it quark, you're wrong because it rhymes with mark. So therefore it has to be quark. So this is where the word quark was invented by James Joyce. And that's its first appearance in the book Ulysses. So we have to ask the question, what the hell is a quark? Well, a quark is the smallest known elementary particle. By elementary particle, we mean a particle that has no internal structure, that you cannot subdivide, if you like, into smaller particles that comprise it. And I put an asterisk by the smallest known because we have to say probably. There have been experiments over the last 20 years that give little tiny indications that even quarks have some sort of internal structure, meaning they may comprise even smaller particles. But none of that has been verified, and most scientists think it's erroneous, that the quark is the fundamental building block of the universe. It's the smallest known elementary particle. So quarks come in six types or flavors, as they're called: up, down, strange, bottom, top, and charm. Now, they're just names. They don't, with the exception of up and down, they don't really mean an awful lot. But they do have these six flavors. And to understand where we would see these quarks, we have to look inside an atom. So a quick revision of what's inside an atom. An atom is made up, the nucleus of an atom is made up of protons and neutrons with electrons orbiting around. Now, before anybody says that's not a correct model, we know that it's not like a mini solar system, that is actually a cloud of electrons and you know, quantum mechanics comes in. Forget all that. Let's just keep to the simple model of protons, neutrons, and electrons. So let's have a look inside protons and neutrons, which is where we find quarks. So here we have some matter as distinct from antimatter. If we look inside a proton has inside it a little bag, if you like, containing three quarks, and it's always three. Two up quarks and a down quark. That's what makes a proton a proton. Apart from its positive charge, it has two up quarks and one down quark inside it. On the other hand, if we look at antimatter, we have the positron, which is the antimatter version of the electron with the positive charge instead of a negative one. We have an antiproton, which is negatively charged instead of positively charged. And we have antiquarks. So we have the same quarks, but they're antimatter counterparts, if you like. And they are indicated by a bar above the representing letter. So we have an anti-up quark. Now, in case you're thinking that an anti-up quark should be called a down quark, no, let's not confuse the issue. They are anti-up quarks and anti-down quarks. So antiprotons have anti-up, two anti-up quarks and an anti-down quark. If we look at a neutron, it's different. Instead of having two ups and a down, it has two downs and an up. But the whole point about it is they're only ever found in threes inside protons and neutrons. Never any fewer, never any more. But does this mean that quarks do not appear in greater numbers than three? No, they do. So we have families of particles with different numbers. We have tetraquark particles. There's a whole family of them that have got 4 quarks inside them. They have an anti-up quark, an anti-down quark, and 2 charm quarks. These are called tetraquarks. Similarly, we have pentaquark particles. A new example of this was actually only discovered a couple of weeks ago, and these have 5 quarks inside them. But these are, if you like, kind of exotic particles that don't last very long, but quickly decay into other particles. And the whole point is the nucleus of an atom is composed of protons and neutrons, inside which you only ever find 3 quarks, hence their association with the number 3. And if you would like more nuclear physics on Space Oddities, because it's all interesting stuff and it all relates to the universe, of course, tell us in the chat if you'd like to see more of this sort of stuff on Space Oddities, because we want to know what you want to see. So there we are. And finally, very briefly, my final 3 is Artemis 3. Artemis 3 is NASA's mission to the moon, which will be the mission to return humans to the moon. It comprises the SLS Space Launch System, shown on the left, that big rocket, and the SpaceX Lunar Starship lander, which will actually do the job of putting people on the moon from lunar orbit. And very quickly, what's going to happen on the left, SpaceX will launch the Lunar Starship. It will be refueled in Earth orbit by, don't know the exact number, could be between 10 and 12 tanker starships, which will refuel it. Then the SLS will launch, and both spacecraft will set off for the moon. The Starship will arrive in lunar orbit first. The Orion spacecraft with the astronauts will arrive afterwards. The crew will transfer from the Orion to the Lunar Starship and descend to the moon to make the historic landing, take off again, rendezvous in lunar orbit with the Orion again, and the crew will return to Earth in the Orion capsule. So that's what's on the drawing board. That's what's going to happen. When is all this going to happen? A tentative date, although I suspect it will slip, of 2027. So we could be seeing humans back on the moon in just 2 years. But what with all the cuts that are going on at NASA and everything, all the other lunacy going on at the moment, then we don't know. So watch this space, as it were. And with that, those are my three related things.
Brilliant.
So there you are.
Thank you, Andy.
Brilliant, Andy.
Hey,
Well, thank you.
Can I just mention, sadly, it's a political statement. Ted Cruz, who is one of the more dominant conservatives in Congress, has said he doesn't like the idea that we're going to give up on the moon and go to Mars. He says we don't want a red Mars. In other words, we don't want the Chinese to beat the U.S. there. So he and other Republicans are pretty strong proponents for getting back to the moon quickly. Who knows how that'll turn out? But.
Yeah, indeed. So there we are. So next up, we have, who's next on the agenda? I think it's Daz, isn't it?
It certainly is.
So Daz, you have got some things for us, I believe.
Yeah, and they're all sort of like
They're
interlinked. Yeah, they're all interlinked. Basically, I'm looking at life cycles of stars.
Right.
Of course, stars, star clusters, and black holes. So,
Okay.
right, if I just pop this up.
Yeah,
There
please.
you go.
Right, keep the votes coming in, viewers. We've had a few in, but we haven't got nearly enough at the moment to declare a definitive window, I don't think. But if anybody would like to
I've been
vote
keeping
on their
account, so
favourite,
we'll. We should
yeah,
have that.
okay, great.
then.
Thank you.
Right. So first
Yeah.
of all, we will start with the life cycle of. Sorry, I just got to get rid of some. The life cycle of stars. Now, the life cycle of stars is exactly like a human life. You have birth, you end adolescence, you have a mature phase, and then you have death. Now, we all know that the birth of stars, they are actually created in massive dust and gas clouds, which are called nebulae or molecular clouds. And they're mostly composed of hydrogen. The star formation happens when a part of such a cloud begins to contract under its own gravity force, pulling the dust and gas together. As the cloud contracts, it fragments into smaller pieces. The collapsing gas in these fragments releases gravitational potential energy as heat.
I know I'm using it as a practice.
Oh,
So here are two molecular clouds, if you want to call them that. You've got the pillars of creation, and you've got star forming in the Rosetta Nebula. And of course, we had a lovely image of that earlier on. So it's all right. I've just got to remember to keep changing my things. We've also got here the Orion Nebula, and in the center, that bright spot in the center, there is a group of stars called the Trapezium. And they're very bright stars, but also there are a lot more stars that are actually forming within this molecular cloud.
see you in a bit.
And some of them have even got to the stage where if you look on the right hand side, you've got protoplanetary disks or proclids within the Orion Nebula. Now, these are stars that have actually grown to the stage where now they're actually now forming a planetary disk around themselves. So these are now reaching the mature stage. So I mean, basically, all you need in here is just a pressure wave to move through one of these clouds, and it will start this process off. And it's all to do with gravity to begin with. So once it reaches, it'll start burning hydrogen. Once it gets small enough and pressure enough, it'll start burning hydrogen in the center. And once that hydrogen has been burnt in the center, then what happens is that center, that core collapses because there's no outward pressure. And then what happens is a shell around the actual center will then start turn into nuclear fusion. Yeah, Tom's just put up fused, but but it is. They actually turns into nuclear fusion as it actually comes around. So it actually starts burning hydrogen first, then it turns to fusion as it gets higher. So, but if the star isn't big enough and it fails, the basically the light will go out and it'll become what we call a brown dwarf. So that's the beginning of it. It then moves into what we call a main sequence star, which is adulthood. Now this is where once the fusion has got going, it will actually burn quite brightly for a while. Then it'll settle down into what we call the yellow sun. Our sun is actually a main sequence star, and there basically what it's doing is it's using hydrogen as fuel as Tom said. Is a nuclear reactor in the center, so fusion of hydrogen into helium. And it will then actually, and how these stars work is that the outward pressure from the nuclear fusion counteracts the actual gravity of all the gas that is surrounding the star, which is basically trying to push into the center, but the actual fusion pushing out actually holds it up. So it reaches an equilibrium. Now, depending upon how big these stars are, as I said, they will go through these stages of burning the hydrogen, and then once they get to the virtually the end of it, they will then start burning. And this is where the elements are starting to be formed. And what will happen is you'll get shells. Actually, as you move out from the side, you get shells of different elements. And once the hydrogen is beginning to fail, you will then the gravity starts to win. This will put pressure onto the core again. But what will happen is the first shell is a hydrogen shell, and this will ignite and start the fusion again. And what will happen is that will give you the pressure to stop it sinking. But as you do this, you're getting more and more pressure. It's getting hotter and hotter and hotter. The pressure out is bigger, so the actual star begins to expand, and then it goes through all these separate shells. Now, again, depending upon its mass, it all depends how it ends up. If you've got a very massive star, I mean, red dwarf stars, which would burn hydrogen in fusion, they will last you for millions and millions and billions of years. They're the longest living. They will last for virtually ever. Then you've got stars like our sun. They will burn for sort of like tens of billions years. We're halfway through the life of the sun at the moment, and ours is destined to go red dwarf at the end of its life. But then what will happen is, but if it's a really massive star, they only last millions of years, because they're so big, they are burning, and the gravity is so immense on the core, and it has to burn the hydrogen a lot faster to keep that pressure to push it out to stop it collapsing, and that will actually only last millions and millions of years rather than actually billions of years. So once you get to the stage where you've done your hydrogen, and there's a lot more things that go on as well, but I'm just trying to keep this brief, is that you will actually see these stars, as they start to burn the different shells, they actually sort of like pulsate a little bit, and they can move up and down the instability strip on the Hertzsprung-Russell diagram, which basically tells you the story of the life of the stars. So now we come to the end. Once you've actually burnt all your hydrogen, all your shell burning's done, we get to the demise of these stars. Now, a star like our sorry, so stars like our own, we will actually it will actually become a red giant star. As the
Daz, can I just interrupt you for a second? You're still on slide 3, by the way.
I keep remembering, don't I? Right, so that's our sun, and as you can see, that was taken just on the 1st of May, and you can see it's all the active regions. So that's when it's a main sequence star. So here's your shell burning. See, I've got to remind me to keep moving these slides. Here's what we're talking about. Shell burning, and you can see the different layers. You start with the shell burning starts with hydrogen, helium, and so on. But the R star will only get to the iron. That's the heaviest element that can actually. That's once you get to iron in the core, the shells, that's when our star will stop burning anything. And then what will happen is the core will actually shrink down, and it will actually form a white dwarf, or what they call a electron star, and then that'll stop. But what it will do is, because as it bounces down, the gas that's surrounding it will close in, and then it will bounce off the core, and it will dissipate out into the interplanetary environment, or the interstellar environment. So it will actually, this one won't go supernova. As you go up in mass, you will actually get the big stars. They will actually collapse, and they will burn all the way up to carbon. Actually, I think I got that round the wrong way. I think we go up to carbon, and then the big stars will go up to iron. But when they collapse, the actual crushing of the atmosphere surrounding the core is so violent that it will actually go off as a supernova, and you'll get sort of like you always see them, the big explosions, and they glow very bright, and they can actually outshine the cores of galaxies where you've got your black holes. So that is what will happen. You'll end up, and the really massive stars will overcome all the, like I said, you've got electron showers. They'll also collapse down. A massive star will collapse down into a neutron star, and they will collapse down into a neutron star. And what basically is when the neutrons get to a stage where they don't want to be together, and they will force their way back again, and they'll stop total collapse. Now, the really massive stars will overcome this resistance, and they will crush right down, and they will actually form a black hole. So you end up with basically three types of sort of like, how can I say, corpses. You'll have a white dwarf, which is an electron star, neutron stars, and then you'll also have black holes. And of course, we know black holes, once they collide, that crush down, they are when light cannot escape. So that's the first one. You've got the three stages of life. You've got birth, maturity, and then you've got death. So that's my three on that one. Now, move your thing on. And here we are. Here we have variations of what they actually are. On the left, you've got a planetary nebula, where it's all been puffed off, and it's formed this big cloud which is being irradiated, and it's actually glowing. And on the right, you'll see 1987 A, which is a supernova, and that is still growing to this day. And 1987 is the year that was actually that actually went off. And I do believe it was in was it in the Large Magellanic Cloud? I don't know.
Yes, it was. Yes.
Yes. Okay, then. So let's see where we got to now. Right. Oh, again, here we are. We're looking at here a white dwarf, Sirius B. As you can see, on the left, you've got an image of Sirius A and Sirius B. Sirius B is actually a white dwarf, and it's basically being outshone by Sirius A. And of course, we remember Sirius as it's the brightest glittering star. And then we've got a neutron star at the heart of the Crab Nebula. So that's on the right-hand side. Right. Oh, and then of course we also end up the third. If they're really massive, you will end up with a black hole. And we'll talk a bit more about black holes. This is actually an image, the very first image of a black hole, M87, and we can all remember when that came out. So I do apologize that I'm not getting the sequence done. So right, now I'm looking at, so we talked about stars. Let's talk about what can happen with some of these stars. So I'm looking at the family of stellar clusters. Right. Now, we all know these sort of these clusters, the globular clusters. These are the gems in this sort of like the cluster family. You got this is M2. As you can see, it's a globular cluster. It's spherical in shape. As you can notice, there are lots and lots of yellow and orange stars in here, because these consist of stars, the oldest stars that we know, and they are up to 10 billion years old. And the reason we know that they're old stars is, one, because their color. But also their metallicity is very poor. That means there aren't many elements in their spectrum. So these are very old stars. They're made from more pure hydrogen and helium. Not much of it has gone on around them when they were first born, to actually make the elements that they would start to burn themselves. So these are very old. You tend to, as I said, they're metal poor. They're usually very old population 2 stars. But also, what you will find in here, which was used to confuse people, is you'll get a group of stars towards the center called blue stragglers. And this was when they tried to plot the actual the spectrums and everything else, the temperatures of all the stars. But of course, all these red stars will be moving off onto the red branch and going up to the red giant stage because they are coming to the ends of their lives. But then they found there was this group of stars that basically they stayed in the main branch in the main sequence line. And what were they've discovered, and it was our friend Fred Hoyle who proposed this, and it's generally agreed, is what's happened is these stars are in pairs, and basically one has died to died and become a white dwarf, but it's actually sat next to a star which is very, very old. It's going into its red giant stage, and you reach a point where the equilibrium between the gravity is overcome, and what will happen is matter will fall onto the white dwarf and will actually make it flare up. So it actually becomes, it looks as though it's a very new star. But all it is it's just collecting the matter off of the old star, which is expanding, and then it would just burn very, very brightly. So it gives us this bit of a confusion why they've got these blue stragglers in them. They're all very densely packed, they're gravitationally bound, and we find them above and below the actual plane of the Milky Way. That's where we find most of these globular clusters. So that's one of the things, sort of like an example, is the Omega Centauri. So we've got the M2 there. We've got Messier 80 again, which is in Scorpius. Again, that's in. You can see so many orange stars there. They're very, very old, and so on. Now, this is what we call a open cluster. I do believe. Let me just check. No, let's go back. This one is actually still a globular cluster. You can see in the center there is a massive group of stars there, but they're considered that they're close enough that it is still a globular cluster. The bright stars are stars that are actually in the foreground, but again you can see lots of different orange stars in that. And I unfortunately I can't read what I've got at the top. It's called Jodorowsky's 1 stars. Right, here we go. So let's move on. The next group, and we all know this one. We saw it earlier on, a beautiful image of this earlier on. We've got what we call open clusters. Now, these are groups of stars that are loosely combined. And what it is these stars were all born in the same molecular cloud, in the same dust cloud. And basically they've blown off most of the cloud. They're traveling through space, but they're still in a group. They're still but they're a loose group. And as you can see, the Pleiades, all these stars are related. There are a lot more stars actually involved in the Pleiades. There's hundreds of them associated with it. And the reason we know that is they've all got the same makeup because they've all come from the same molecular cloud. And these can vary. They can tens of thousands of stars, but they can't. They're less dense. They're water. They're looser. So usually they're younger stars. That's why they're a lot brighter. So we get these really bright stars. You don't see many orange ones in there. So this proves that they're actually younger. And also, they're when you look at their metallicity, they've got far more elements actually inside them, which means that they are burning in nurseries which had far more elements inside them, and that can only come from dead and exploding stars. So where they've puffed off their atmospheres or they've exploded, spreading their life's work, the elements that they've made into the atmosphere, and then they're picked up by these new stars. Now, the next group of let me just have a look to make sure I've done that. Now this is a group of stars. Now I love this group, I really do. It's just to take a photograph of it. This one doesn't actually do it justice, but it's called the Hyades, and you can see it with the naked eye. It's in Taurus. You can see Alba on there, which is the eye of the bull. But this group, when you take a photograph of it using an SLR or whatever, it suddenly pops out at you and you can see it. It's a very, very loose group, but it's got so many different colors within it. And it really does look spectacular. Now, this one is getting to the stage where they reckon that the dispersal of the actual stars is getting to the stage where it will actually turn into the next group, which I will talk about in a second. So here we are, and this is what they're called. They're called stellar associations. Now these are spread over light years. But what? Oh, excuse me. But what it is all these the stars within these groups have been analysed. The spectrums have been done, and they're all associated with each other. But this is as you can see in this image, this is where you can find them. They're spread out throughout the hemispheres. And you can see that these groups, some of them are absolutely massive, but they are all associated with each other. Now, these are also spread into 3 groups themselves. And excuse me, I've just lost my page. So this is what we're looking at. They're called stellar associations, and what they are, the stellar associations are described as a group of stars that share an origin but are less tightly bound than open clusters. They are considered a third variety of stellar grouping, more dispersed than globular clusters. They are most dispersed variety of stellar grouping. Now these stars, they basically they can actually be in. They can either have tens of thousands of them. But these, some of these associations are up to 700 light years across. They contain mainly young stars because of their common origin. The stars have similar ages and metallicities, as I said. You'll find them in the Milky Way, and they're drifting. They're also called moving groups, and they actually are moving through the solar system as they go. But they all seem to keep within themselves, but they are slowly dispersing. And as I said, they can be categorized themselves again by their makeup of type stars. You've got OB associations. I'm not going to go into what they are. T associations and R associations. And basically, as I said, one of the most obvious ones is the Orion OB1 association. Yeah, I know OB1, and that is actually a big group of stars that are based on the Orion. And I think I've got a picture of this. There we are. There's the Orion one, and you can see it's based on the belt and the sword, and the other stars actually all linked into there. So you can see that there's OB1A, OB1B, and things like that. So yeah, these are really big groups, but they all are found to have a common ancestry. So I think it's best to leave it there. So we've got globular clusters, open clusters, then we've got stellar associations, which are cover absolutely huge areas of the sky. And lastly, I'm not going to go too much into this because I've taken up too much time. I tend to be waffling. So what we will do is we'll move on. What they call one of the stellar associations is in Ursa Major, and it's a moving group, and it's the closest moving group to Earth. So black holes. Now we know that I've said that these black holes can form by the collapse of stars if they're massive enough. Now I know that people are going to say I'm leaving out a group of stars, but I will come to that at the very end. So basically what happens is these black holes are areas where things have actually grouped together. The gravity that is combined, and they've literally crushed themselves down into an area where even light can't escape. But the only way we usually can detect them is what's happening around them. If we see, like in the center of the Milky Way, we studied the stars in the closest to the center of the Milky Way, and we could see how they were they were interacting with something that we couldn't see, something that had a massive gravitational effect on the stars, and they were actually orbiting them. And that's because we couldn't see it. Of course, we now know it's an actual black hole. So we start off with stellar mass black holes. These usually form from stars that can be 3 to 50 times the mass of our sun. The abundance of stellar mass black holes are considered common. Scientists estimate there could be as many as 10 million to a billion in the Milky Way alone. Their formation, they form partially from the gravitational collapse of single massive stars at the end of their lives. Only the massive stars will actually become black holes through this process. Stellar black holes can also form from the merger of two neutron stars. Growth and formation. After formation, they can gain mass through collisions with stars and other black holes, or by pulling gas off of a companion star. Detection, again, as I said, it's by us studying the environment around these areas, or we will actually be able to see in different wavelengths the accretion disk if it's an active black hole and it's actively feeding. It would glow so it glows so bright that we can actually detect them. And I do apologize, I'm waffling. Then we've got intermediate black holes. Now these are rare, very, very rare, and the reason I've introduced them is that their existence was predicted, and it's only just sort of like recently that we've actually been able to possibly detect them. We found possibly a intermediate. Now these are when I say intermediate, they go from these are linking between stellar black holes and supermassive black holes. So this is sort of like a missing link between the two. And of course, we've got to remember is that we don't know how these stars form. So this is why detection of them, because don't really know what we're looking for, is so rare. But we have found possibly a couple of candidates, and one of them is in 3XMM 1215022.4-055108. That really rolls off the tongue. We'll call it Dave. And it's estimated to be 50 solar masses. So they think that they've detected one in there. And also we've decided that we've detected. And again, these are one of the theories is that you will find these in globular clusters. So when we go back to the globular cluster, and one of them that they think they've possibly detected an intermediate black hole is an Omega Centauri. Which is and they reckon it's got a mass of at least 8,200 solar masses. Then we've got the supermassive black holes.
Daz, your slides are moving on, by the way.
Thank you very much. Thank you, Andy. Oh, also, people put a message up, probably telling, get on with it. So this is a simulation. Is it running? Oh, no, it's not. Is it?
No.
It's not running. Sorry, but this
No.
was a GIF, and it was showing whole stars actually circling around a object that we cannot see in the center of where it's shown us where the black hole actually lies. It was around about here, so we'll ignore that one. The globular cluster male 2 MG31 is a possible candidate for hosting an intermediate black hole. And also, this is RXJ1140.1, looks like plus 0307. Sorry, I've got something over the top of my actual label. And this is a galaxy. And again, they think that the center of this is a galaxy that's formed itself around an intermediate black hole. And then we've got This is Omega Centauri. Look at that, that's a beautiful globular cluster. And this is where they think that they've actually found possibly indications that there is a black hole at the center of this globular cluster. So here we have the central region of Omega Centauri. The lower illustration charts the future positions of the stars. So this is where they're going to be moving to. And you can see that it's this little box in the center. Each streak represents the star's predicted motion over the next 30 odd years. And you can see there is, in the center, there is an area where stars are going off at all different angles, but they're actually forming a circle around a area right in the middle there. This is an art impression of a supermassive black hole surrounded by an accretion disk, and again, when these things are feeding, you get you get jets form. But how we can detect them is because of the actual energy that's being created actually in the accretion disk. So I think I've got an image here. This is at Messier 87. Now I showed you a picture of this earlier on. This is a Hubble telescope, and what you can see from you is one of the jets actually coming towards us. It's not directly towards us, because then we're talking about blazars and other things and things like that. So this is the actual jet that we were talking about. So we know in the middle of M87 is a huge black hole that is feeding, and this is that image again. And you can see there are actually lobes where so you can detect it. Now, the actual dark spot in the middle is not the black hole; it's its shadow. What we're actually looking at is the accretion disk. The actual singularity is right in the middle there, and it's so small that, well, like we said, light cannot escape it. It's basically what we're looking at is what we call the shadow. So there we go. Again, this is the orbits of the stars in the center of our galaxy, and you can see they were orbiting, and they all seem to be based around this one spot in the center there. So this is how we detected the black hole at the center of our galaxy, Sagittarius A, and of course we've actually imaged that as well. So this is the center of the Milky Way galaxy with a supermassive black hole at the center. I'm going to stop there because I'm taking up everybody. Oh, and this is just other images of supermassive black holes that have been ejected from their galaxies. So, oh, sorry, I've lost my cursor. So there we go. So there you go. I hope that explains it. So we've got stellar black holes, intermediate black holes, and then we've got supermassive black holes. Now, the one that people will be shouting about, what about primordial black holes? We've never found them. They are hypothesized, and they think they were created at the beginning and just after the Big Bang. And this will, but we've never actually found them. So I'm just concentrating on the three that we think, well, we've got good evidence for. So that's where we go. So sorry for waffling, sorry for going on a bit too long, but that's my threes.
Great, thank you, Daz. Very kind. I hope you enjoyed that, audience. I think at this point, what we're going to do, I see the voting for the images has more or less stopped now. Any final votes coming in for the image to win a T-shirt? Well, the photographer of the image, obviously, not the people who vote. We might do something for everybody at one point if we have enough donations and we can get our act together. Give you all a prize, which we'd love to do because you're a lovely audience. So let's have a look. Has anybody been keeping tabs on the voting?
I've just noticed that there's one more since I've been waffling on. So I'm keeping count.
So what we're going to do now, just give me 1 second, and I will just sort, while you're counting those up, I will just sort the visuals out. Okay. All right. So just give me 1 second, and we'll put the images back on the screen. We'll go through them. We'll tell you whose images they were, and then we can reveal the winner at the end. So here's your image number one again. This was by Jerry Delay. Lovely image, Jerry. Round of applause for Jerry, because that's quite a stunning image. Yep. Number 2, Kenneth. Well done, Kenneth.
Lovely
Again,
shot.
smashing
Lovely,
image of M98. Number 3, again by Kenneth again. These were all chosen at random, so so don't blame me, blame the computer. Again, Rosette Nebula number 3. Jerry again for number 4, the Pleiades.
Lovely.
Dave Garside took image number 5 of M51, and we had another M51. Michael Murphy, M51. Well done, Michael.
Lovely.
Fantastic. Lee Hall did the lovely Call the Doctor image, very creatively, as always.
Very magical.
Love that one, number 7. Jerry did number 8, the Horsehead and the Flame Nebula. And Lee again, number 9, the Star Trails. And number 10, Kev Earp did the wonderful Lunar South Highlands. So, big moment, big drum roll, I suppose. Daz, would you like to tell us who the winner is?
The winner is number 8.
Number 8, Jerry Delay. Jerry has won the coveted prize of the Space Oddities t-shirt. A round of applause for Jerry.
Well
Well
done.
done.
Very well done, everyone, because the images we get every week are fantastic. Love seeing
Yeah.
them.
So what you should do, Jerry, go to the Space Oddities shop. Let me just put the link up if you're watching. I don't know if you're here tonight, but if you are, I'll just put the Space Oddities shop link up here again, if I can do that. There we are. So if you look in the chat, it should have appeared in the chat. Click that, go to the shop and tell us which design you want and which size t-shirt you would like. And then if you'd like to drop us an email at info@spaceoddities.space, and with your details, your address and everything, and which t-shirt you want and the size, we will get it off to you as soon as we receive that. So congratulations, Jerry. You've just won
Cheers for
yourself
that.
a Space Oddities
I don't know if you
t-shirt.
saw earlier, Andy. I think Anne was asking for a link
QR
to be
code
put up
again.
earlier.
Which one? Which code?
I don't know. I'm trying to find her original.
Well, let's put them all up again.
Yeah,
Then. It's easy. So here's the buy us a coffee link. If you would like to contribute to Space Oddities by buying us a coffee, you can scan the QR code or you can click the link that's just appeared in the chat. And well, we've just had the Space Oddities shop one. I'll just go through the others actually. Space Oddities t-shirts. You can click the link if you want to buy a Space Oddities t-shirt directly. And there we have the Space Oddities hoodies as well, which are £40. The t-shirts start from £25. The hoodies are £40, including UK postage and packing. All the prices include UK postage and packing, by the way, on the merchandise. So it's a good deal. If you're outside the UK, then please add £10 to the total value of your order to cover postage and packing to another country. So there we are. So we have a winner, Jerry Delay. Obviously, we'd like to thank everybody who contributes to the gallery again. And I hope you've enjoyed, if you were included in the computer's pick for tonight, I hope you enjoyed seeing your images again. We certainly enjoyed looking at them again. So there we are. Okay, we're going to move on now to Roger. So Roger, it's your turn to tell us all about threes. And which one is it? First one. Because you've got a few up here, I see. Can't hear you, Roger. No, can't hear you. Okay, seeing a problem with Roger's sound. So while he's sorting that out, Lou, can we come to you?
Yes, sir, that's fine.
Okay, great. So let me just put your presentation up here, Lou. Let me just hang on, just let me get rid of the QR code off the screen. Oh God, where's it gone? 1 second. Okay. I'm all fingers and thumbs tonight. It's the excitement of the event. There we are. Okay, so let's now put this up on the screen for you.
There we go.
So there we are.
Okay. 3 cool space topics, and we're going to try to do each one in 3 minutes. So let's get into it.
Whoa,
Yeah,
good luck with that.
I think I may falter here a little bit. Okay. The first one is the triple alpha process. This is the nuclear fusion reaction that takes place in the cores of red giant stars, fusing helium into carbon. Once the star has ceased hydrogen to helium fusion in its core on the main sequence, the core contracts under the now unchallenged force of gravity until its temperature reaches about 100 million degrees centigrade, if you can imagine. At that point, the star can begin to fuse helium into carbon, a process known as the triple alpha process. And this is a key stage in the stellar evolution of red giant stars. This is a graphic of the triple alpha process, a graphic representation. Here you see 2 helium nuclei called alpha particles. That's the key. And they form into beryllium-8. Now, beryllium-8 is unstable. It's an unstable element with about a half-life of 10 to the minus 16 seconds. In fact, there are no stable elements with atomic numbers of 8 or 5. So it's unstable. But during that brief period where it exists, a third helium nucleus collides with beryllium-8 to form carbon-12. Each of these interactions releases a gamma ray photon, which powers the red giant sun. Notice here, however, no neutrinos are created, and that'll be important later, so just hang on to that. No neutrinos are created in red giant stars. Sir Fred Hoyle, pictured here, 20th century English astronomer, formulated the theory of stellar nucleosynthesis and calculated that the triple alpha process would require the carbon nucleus to have a very specific, yet as yet unobserved, resonance energy and spin for it to work. But he was later able to successfully identify this energy level and quantum spin. And that is how red giants shine. My next topic is the Alpha Centauri triple star system. Ta-da! Here's a chart showing the relative sizes of the 3 stars in the Alpha Centauri system, Alpha Centauri A, B, and C, which is called Proxima Centauri. Alpha Centauri A, or Rigil Centaurus, I think that's how it's pronounced, is a main sequence star, spectral type G25. Star has a mass of 1.1 solar masses, pretty close to our sun, a radius of 1.2 times our sun, and an effective temperature of 5,790 degrees Kelvin. So it's 1.5 times more luminous than the sun. So small changes in temperature, this is called the Stefan-Boltzmann effect or Stefan-Boltzmann equation, produce large changes in luminosity. So we see here that that's the case. And you'll see this in the other 2 star systems, other two stars as well. Alpha Centauri B, or Ptolemy, is a bit smaller and less massive than Rigil Centaurus. With the stellar classification of K15, it appears more orangish in color. The star has a mass of about 0.9 solar masses, a radius of 0.86 solar radii, and has a surface temperature of 5,260 degrees. Our sun's surface temperature is a little more than that, 5778 Kelvin. And so Ptolemy has only 50% of the sun's luminosity. Alpha Centauri C, or Proxima Centauri, is a red dwarf star with the spectral type M5. It has a mass of 0.12 solar masses. It's quite small, and a radius of 0.15 solar radii. With an effective surface temperature of only 3,000 degrees Kelvin, it shines at only 0.0017 solar luminosities. So it's about 20,000 times dimmer than the sun. There we go. What you're seeing here is a graphic depicting the orbits of Alpha Centauri A, B, and C. Centauri A and B orbit each other at between 11 and say 36 astronomical units with an orbital period of about 80 years. But Proxima Centauri is 12,950 AU, or about 0.2 light years away from the very center of A and B. So it has an orbital period of 550,000 years, and obviously a very eccentric orbit of eccentricity of about 0.5.
God. How did it get so eccentric? That's mad.
I don't know. They say that multiple stars form in large. See, now this doesn't count for my time. Okay, multiple stars form in supernova molecular clouds, and it may be that our sun's twin, is one of these stars.
Yeah.
Hard to say.
Wow.
But there's more.
There's more?
There is more. It turns out that Proxima Centauri has at least one, and possibly three, but only one confirmed planet around it. This planet is orbiting in the Goldilocks zone, the habitable zone, which means liquid water could exist on the surface at about 0.05 AU from Proxima Centauri, and an orbital period of 11.2 days. But look down here at the physical characteristics. Its mean radius is about the radius of the Earth. Its mean mass, its bulk mass rather, is about the mass of the Earth. Its temperatures are a little bit on the cold side, but nothing we couldn't survive. I think this would be a good place when we destroy our Earth, or it gets destroyed for us. This might be a place to go and look. And up in the upper right, by the way, is the chart of the radial velocities of the planet of the star as the planet pulled on it in its orbit, and that was the detection.
Yeah, wow.
Yeah.
Interesting.
Let's go to my third topic today, and that is the case of the missing neutrinos.
Dun, dun, dun.
Come on, who nicked the neutrinos? Oh no.
Well, that's very clever, right? We don't say nicked in America, so I wouldn't have thought. That's very good. But I'm learning. I'm learning my British. I'm learning. So bear with me, please. It turns out that we thought the sun was missing some of its neutrinos. The problem of missing solar neutrinos was a long-standing mystery in physics, where the number of neutrinos detected from the sun was significantly lower than that predicted by the standard solar model. And the standard solar model, which we'll see in a moment, is one of the most complete and successful theories in modern astronomy. And it has 4 concepts to it. The first is the sun evolves in hydrostatic equilibrium. This means there's always a balance between fusion pressure pushing out and gravity pushing in. The second, energy can be transformed in the sun through a variety of ways: radiation, conduction, convection, as well as neutrino loss. The third, thermonuclear reactions are the only source of energy production inside the star. And the fourth, the sun was initially part of a homogeneous molecular cloud of primordial composition, and that when it joined the main sequence, when it turned on, when it first started fusion, a time called the ZAMS. If you haven't heard that before, that stands for Zero Age Main Sequence. It was a highly convective star, and that convection still goes on today. In the late 60s, physicists observed that solar neutrino detectors on Earth were detecting only about a third of the, see, there's the number 3, of the predicted number of neutrinos. This difference, known as the missing neutrino problem, baffled scientists for decades. This discrepancy in numbers of neutrinos observed versus predicted was attributed to neutrino oscillations. This is where neutrinos change their flavor or type during their journey from the sun to the Earth, making them undetectable, or making many of them undetectable. The three types of neutrinos then are electron neutrinos, muon neutrinos, and tau neutrinos. And during nuclear fusion, the sun produces primarily electron neutrinos. But again, as they travel through space, they undergo a flavor oscillations. So they change into muon and tau neutrinos. Who knew? Here is the a graphic of the process, the proton-proton reaction inside the sun that makes the sun shine. Just quickly, the two hydrogen protons fuse into deuterium, releasing a neutrino and a positron. Deuterium and hydrogen make tritium, and two tritiums make helium-4, liberating two hydrogen nuclei. The standard model then predicts a specific flux of neutrinos based on this nuclear fusion reaction. But again, experiments such as the Davis experiment, which used chlorine-based detectors, or the Super Kamiokande experiment, which we just call Super K, using large water tank, they consistently detected a lower flux than predicted. So we detect neutrinos here on Earth by observing their secondary particles that are produced when they interact with matter. And we also observe what's called Cherenkov light, or Cherenkov radiation, which is light that is traveling faster than it should in a dense medium. Since neutrinos are neutral in their charge and weakly interacting, they rarely interact with other particles. You've got millions of neutrinos flooding through your body every second and no effect, right? But when they do interact on rare occasion, they can create a shower of secondary particles, which can then be detected by various methods. These detectors are generally buried deep inside the Earth to eliminate cosmic ray and other background radiation effects. And I would be remiss if I did not show you this picture. This is a picture of the sun taken at night through the Earth. This picture was constructed with the Japanese Super K neutrino detector, which we just talked about, looking at neutrinos that are traveling through the Earth. And because, again, the neutrino oscillations and detections are very rare, it took 500 days worth of data to produce this neutrino image.
Wow.
Amazing.
It's amazing.
The sun is centered in the frame, and the picture covers a large piece of sky, about 90 by 90 degrees in right ascension and declination. Brighter colors represent larger neutrino fluxes, dimmer colors less so. And that is my presentation.
It's amazing.
Thank you very much, Lou. Fascinating stuff. Of course, there's another point to come out of the three flavors of neutrinos.
Is it chocolate?
And that is...
Oh, sorry. I'm sorry.
So, oh, yeah. It used to be thought that neutrinos were massless particles. But when they discovered that they were changing their flavor en route from the sun to the Earth, that could only happen if neutrinos have a tiny amount of mass. So it was a double discovery, if you like, that neutrinos actually do have some mass. Yeah. Great. Thank you very much, Lou. Right, Roger, can we hear you now? No. Oh, okay. That's a shame. Right, he says he's. I think I'm good at lip reading. He's going to come out and come back in again. Either that, or he just ordered a vindaloo with pilau rice. I'm not quite sure. So Roger, we've lost Pete Williamson has had to go because his laptop battery died. Tom has had to leave us as well because he has other commitments. So thanks for coming along, guys.
Lovely seeing you.
And a big thanks to Pete Williamson for kicking the ball, starting the ball rolling as far as SpaceOddities went when we migrated to YouTube from Astro Radio when Astro Radio ended. And I've been stuck with this lot ever since. You get less for murder. So there we are. So okay, let's let Roger back in, shall we? Yeah, go on then. Well, it's our third
Oh, it's
third
our
anniversary.
birthday, yeah.
So
well,
go on then. Right, can we hear you now, Roger?
no.
Not really. No.
How strange.
Yeah, I know. He's having sound problems this evening, obviously. Paul says, yes, wow, a picture of the sun taken through the earth. Amazing. It is an amazing image.
That
Paul.
was astronomy
Absolutely.
picture of the day some days ago. I forget exactly how long. Yep.
Oh, was it?
Really gorgeous.
Right. So yeah. So thanks for that, Paul. Indeed. And neutrinos, of course, are incredibly mysterious particles. I mean, you know, we know a bit about them, but they are called the ghost particles of the universe because they pass right through the Earth without even noticing it's there. And in fact, trillions of neutrinos are passing through your body, everybody's body, as we speak, and they go through your body like it wasn't there. So they are extremely interesting particles.
You know, we're going to have a debate at some point on this dark matter versus MOND idea. And
yes,
I don't know where this stands, but I know that depending on the tiny, tiny mass of the neutrino, it is possible that accounts for that. Perhaps it is the dark matter particle. Are you aware of where that stands? Is that still a reality?
It's been one suggestion, but I don't think it's got much further than a suggestion at the moment. So but we will look into it.
I will strike it down then when I.
Yeah. Okay. We are going to do a debate on Space Oddities, the whole dark matter versus MOND debate. And we hope you join us for that, because that should be quite interesting. Anne says she loves neutrinos. Yeah, I'm sure they love you too, Anne. So there we are. Right. So let's see if Roger, can you say something now? No, he's still not there. Still not there.
That's
No,
sad.
I don't know what's.
Well, we do need material for next week. I mean, I think this isn't all bad.
Well, that's right. Yeah. So Roger has obviously got sound problems. So not sure what's going on there.
You can just
Roger.
put up your pictures and we'll take turns, like trying to imagine what they're about.
Yeah. I'll just check your volume. Your volume level here is fine. Everything's fine as far as you're concerned this end. So I don't know. The only thing I can suggest, and you're going to hate me for saying this, have you tried turning it off and on again? So yeah. So that Roger will be rebooting. So Anne says, ever heard of a neutrino hitting a particle in a human, and how would we know?
Well, it would be right. So the odds of that happening are amazingly close to zero, but not zero. There's a lot of water in us, and it would create some other particles. I guess I don't know how we would figure it out. I don't think it would cause cancer, but because it's going to have one interaction with one molecule. But I don't know. Anne, would you look that up for us, please? We don't know.
Unless you put thousands of tiny photomultiplier tubes inside the human body to detect the Cherenkov radiation, they would cause that tiny flash of blue light when they strike a water molecule, because it does happen, because this is, after all, how they are detected. And neutrino detectors, there's a huge one at the South Pole, and called IceCube, which they're just applying for more money. It looks like they might have got it, although it comes from the National Science Foundation. So, but they have applied for more money to double the size of IceCube. It's a massive neutrino detector, and also, of course, there's one under the Mediterranean, off the coast of Italy, which has neutrino detectors on these long strings, going down to some considerable depth in in the Mediterranean. And so neutrinos are worthy of study because they are seriously, mysterious. Also, if you go back to something that Daz was mentioning earlier, supernova 1987A, the Super Kamiokande detector in Japan detected 13 neutrinos from that supernova explosion. But it didn't detect them until after the event. They didn't even think to look until after the event. But what they found was that the neutrinos had arrived before the light from the explosion, conclusively proving that neutrinos are emitted from supernovae explosion before the actual explosion. A few hours before the actual explosion is when most of the neutrinos get released. So that was a bit of a discovery in itself, and we've seen this in other detections of neutrinos from other events arriving before the visible light does, and there we are. And if you think about the gravitational wave event GW 170817, which was the first multi-messenger event when it was detected first through gravitational waves, a collision of two neutron stars, first through gravitational waves, then gamma, then X-ray, right across the spectrum. And the final detection was radio waves 13 days after the collision of the neutron stars, which demonstrated again this time lag that different particles get emitted at, and different radiation gets emitted at different times in these events. And that tells us a lot about the events themselves. So there we are. Yes, Daz said, yes, Ian, there has been no Einstein of the week this week. You haven't missed anything. Basically because I haven't seen anything this week worth adding into Einstein of the week. But I'm sure we will be back next week with more. Okay. Mick says, Anne complains when I do nothing, but yet she loves neutrinos. Yeah. Well, I think we'll allow that, Mick.
Yeah. And also, I think that's. I hope the settees, they're comfortable. The sofa's comfortable tonight.
Yeah, that's right. Yeah, you have got a comfortable sofa. I can attest to that. So there. Okay, Roger's back in, and can we hear him now? Roger.
Oh, got something there. Point your face toward the speaker. Well, something.
No, still nothing. Right. Well, in which case, I think what we will do is we will leave your presentations until next week, Roger. We will show them next week. We will carry on with this.
Get Amazon to overnight you a microphone.
Yeah. Yes, but perhaps we can buy you a new microphone, not a new computer.
Or a semaphore machine.
So, yes, that's right. Which also means that Constellation of the Week will be put back until next week because Roger was doing Constellation of the Week this week. So we'll put that back to next week.
But it's one we can pronounce anyway. So
yeah, that's right. We've got a week to practice it. So there we are. All right, then. Listen, we will start therefore drawing things to a close for this evening. As it's now we've been streaming now for 2 hours and 2.25 hours just about. We would like to thank every single one of you for being here tonight to share this special edition of Space Oddities, our 3rd anniversary, with us. We would especially like to thank you for your kind donations of money towards keeping Space Oddities going into our 4th year. It's been a lovely evening. We hope you've all enjoyed it. I think we covered a fair variety of material tonight. But Jerry DeLay, congratulations on winning the T-shirt. I'm sure Roger has your email address. So if we don't hear from you, Roger will email you, and he'll tell you all about it. So there we are. Now we are going to come back next we'll be back later tonight, in fact, on Space Oddities, because in a few hours it's the launch of SpaceX's Starship on its 9th test flight. Very important flight for SpaceX, because as you probably know, that the previous 2 missions ended in the Starship exploding. So there's a lot riding on this one. SpaceX have got to prove that the Starship is a viable vehicle, especially as the lunar variant of Starship, as I said earlier, will be the vehicle to land humans on the moon again, hopefully in 2027. This is a very, very important flight. So we hope you can join us. Launch is scheduled for 12:30 UK time. So we'll be back later. We're going live at 12:15, 15 minutes before the launch. So you've got, just over an hour or just under an hour to grab yourself a coffee and join us again at 12:15 UK time, when we will bring you live coverage of the 9th test flight of SpaceX's Starship. It's going to be an interesting mission. SpaceX have made lots and lots of improvements to try and stop the vehicle exploding again. They know what caused the 2 previous explosions, and they weren't due to the same thing. They were completely unrelated causes. So let's hope they've done enough so that Starship doesn't explode this time. They really need this mission to succeed to demonstrate that they have a viable space vehicle with the Starship, which we believe they do, but it's proving to be a bit of a tough nut to crack, as with all rocket development programs. So join us again.
Sorry, I've just checked and it is still on at the moment.
It's still on, right? Fantastic. So join us later, viewers, at 12:15 UK time. That's 1:15 my time, so I'm going to have to stay up late tonight. But what the hell? It's a SpaceX Starship launch. They don't happen that often. Although they do have permission now from the FAA to launch 25 Starships per year. So you can expect the launch frequency to be ramping up. And we hope you can join us for that. But thank you so much for being here this evening. We hope you've enjoyed yourselves. Lovely to see you all. And Gerard especially, get well soon, mate.
Yes.
Keep smiling.
And Andy, you can stay up because it's our 3rd birthday. So,
well, absolutely. I just need a coffee. That's all I need. So I will.
and some matchsticks.
I will. Yeah. I found out last night. I was doing something. I was desperate for coffee. Found I run out of coffee capsules for the
You're
machine.
not very well
but I had
organised,
some.
are you?
No. I know. I usually am, but yesterday I wasn't. But I found some tea bags. I thought, oh, I'll have a cup of tea. But they turned out to be Spanish tea bags. And Spanish tea bags are so weak that you can leave the teacup in the tea bag in the cup for 10 minutes and it still looks like milk. So it wasn't nice. Anyway, I digress. Thanks for being here, viewers. Hope you can join us again at 12:15 UK time for the launch of SpaceX's Starship. But from all of us, a big thank you for being here. From Daz, from Roger. Sorry, Roger can't say goodbye. From Lou, thanks for your contributions, guys. Thank you for being here too. And we hopefully see you at 12:15 UK time. If not, we'll be back same time, 8 p.m. next Tuesday for another edition of Space Oddities. So if we don't see you later, have a fantastic week. Look after each other. And thanks again for everything.